Today, we're tackling a real chemical head-scratcher. We're going to look at a molecule that, on paper, really shouldn't even exist. It's called diborane, and it seems to completely ignore one of the most basic rules of chemistry. So let's just get right to it. How can a molecule possibly hold itself together when it literally doesn't have enough electrons? I mean, we all know a standard chemical bond needs a pair of electrons, right? So what gives? This is the core puzzle of diborane. All right, let's break this down. Think of it like a little chemical detective story. The first thing we need to do is look at the evidence. And in this case, the evidence is the molecule's own electron count. So here's our molecule of interest, diborane, or B2H6. It's a really important compound in boron chemistry, but the thing everyone knows it for is being electron deficient. And figuring out what that really means, well, that's the key to this whole thing. Okay, let's just do a quick count. You've got 2 boron atoms, and each one brings 3 valence electrons to the table. Then you've got 6 hydrogens, each with 1 electron. So 3 plus 3 is 6, plus another 6 from the hydrogens. That gives us a grand total of 12 electrons to work with. That's our entire budget. Now here's where it gets weird. If you tried to draw this molecule the normal way, like its well-behaved cousin ethane, you'd need to connect all 8 atoms. That would take 7 single bonds. And since every bond needs 2 electrons, well, 7 times 2 is 14. You'd need 14 electrons for that structure to work. And there's the problem, plain as day. We have 12 electrons, but we need 14. We're running a deficit of 2 electrons. So I'll ask again, how on earth is this thing staying together? It feels like it should just fall apart. So this electron shortage isn't just some number on a whiteboard. Oh no. It has some really dramatic, real-world consequences for how diborane acts. Let's look at its behavior for some more clues. Yeah, this molecule is not stable. Not at all. It's super reactive. It's pyrophoric, which is a fancy way of saying it can just burst into flames in the open air. It also goes absolutely nuts if it touches water. And see, these aren't just quirky personality traits. They're giant red flags screaming that this molecule is desperate to grab the electrons it's missing. Let's talk about that pyrophoric thing for a second. The moment diborane hits the oxygen in the air, boom, it reacts, releasing a huge amount of energy. We're talking over 2,000 kilojoules per mole. That's a massive release of heat, and that's why it can just ignite all by itself. And it's not any happier around water. Put them together, and you get a violent reaction that spits out boric acid and flammable hydrogen gas. Again, all this chaos, all this reactivity, it all points right back to that unstable, electron-starved structure. Okay, so we have our mystery and we have our clues. Now for the big reveal. How does nature solve this problem? Well, the answer is genuinely one of the coolest and most creative solutions in all of chemistry. The trick here isn't something you can see with a simple Lewis dot structure. We have to go a little deeper, into something called molecular orbital theory. So here's what happens. Boron gets ready to bond by doing this thing called sp3 hybridization. Now that sounds complicated, but all it really means is that it shuffles its electron orbitals around. When it's done, it has 3 orbitals with 1 electron each, ready for normal bonds. But, and this is the crucial part, it leaves 1 orbital totally empty. And that empty orbital, that's the secret sauce. That empty slot opens the door for something pretty mind-bending, a 3-center, 2-electron bond. Think about it. A normal bond is 2 atoms sharing 2 electrons, but here you have 3 atoms, 2 borons, and a hydrogen in the middle, all sharing just 2 electrons. It's like they're stretching those 2 electrons to do the work of 4. It's incredibly efficient. And because the path these electrons take is this sort of curved arc, chemists gave it an amazing nickname, the banana bond. And diborane has 2 of these banana bonds, holding the whole thing together like a bridge. And this isn't just a theory. We can actually see the evidence with X-ray analysis. The data clearly shows 2 different kinds of bonds in the molecule. You've got the 4 normal hydrogen bonds on the outside, the terminal ones, which are shorter and stronger. But then you have the 2 hydrogen bonds in the middle, our banana bonds, and they are measurably longer and weaker. That difference is the smoking gun. It proves that those 2 electrons are being stretched out over 3 atoms. So we've cracked the case of its structure, but how do we actually make this stuff in a lab? I mean, with how reactive it is, you have to wonder how anyone makes it without things exploding. Well, on an industrial scale, it's done through a really carefully controlled process. Chemists react boron trichloride with a super powerful reducing agent, lithium aluminum hydride. This lets them make diborane gas efficiently and safely, and that gas is then used for all sorts of things, including as an ingredient in rocket fuel. All right, let's wrap this up. What's the main takeaway here? What makes diborane so fascinating? So the big idea is this. Diborane isn't really breaking the rules of chemistry. It's just playing by a different, more advanced set of rules. Those two banana bonds are the perfect, elegant solution to its electron problem. And that unique structure is both the reason it can exist in the first place and the reason it's so incredibly reactive. And that really leaves you with a cool thought, doesn't it? Diborane is a perfect reminder that the simple rules we learn in chemistry are sometimes just helpful starting points. It really makes you wonder, if molecules like this exist, what other amazing, impossible structures are out there, just waiting for us to find them?